Hi, good afternoon. The lecture that you heard last time on Tuesday had to do with the important topic, certainly one of the most important 2 or 3 topics in the MOS device physics, and that has to do with short channel effect. You remember that, right? If we briefly review what was done, I would highlight the quasi-2D model of this effect. Some may call that Dibble effect. Now, of course, we did talk about other ways of thinking about this phenomena, such as just using 3 capacitors. But I highlight this quantitative model as the main point of last lecture, and you should soon, if you have not yet read it, soon read this reference, IEEE article. And the analysis basically found a solution for the potential profile of U-wheeled energy band diagram between source and drain along the surface of the channel, all right, basically. And from that analysis, we concluded that delta VT, which is the roll-off of the threshold voltage, is a linear function of VDS. Actually, it's proportion of VDS plus some number around 1 volt. And it's an exponential function of channel length. It's capital L, right? If channel length is large, then we have very little VT roll-off. If channel length is small, we would have large VT roll-off. Large and small relative to what? Relative to a quantity that we call the decay length, right? This lowercase l, which is equal to 3 Tox XD max. Now, I put a approximate sign there because it's approximate model. We picked a boundary for the Gauss box at the bottom as a line at XD max, but we all know in short channel transistor it's not XD max, or even if it is, we don't know what it is, right? It has to do with the source string junction depths, and so it's kind of approximate. And the reference that I asked you to read will give you another formula for this decay length that's empirical, that's a result of experimental study and device simulation studies. And it confirms that has to do with oxide thickness and XD max, and also have some impact of XJ represented. And I think you can probably visualize where XJ might come in. If we have large XJ, it will push the bottom boundary away, first of all, right? And using the well, I would not force this topic too much right now. It's a review, so I would just stop there. So you can think that there's also some impact of XJ, such that in order to suppress the short channel effect, we want thin oxide, we want small XD max, we also want small XJ. That's what we want. All right? Now it's interesting if you put the typical numbers into these 2 formulas, they don't differ that much. Certainly it's within the kind of, say, even the experimental error that you can determine just by casually look at the data between delta VT and channel length. From that data, you kind of can estimate L, this decay length, right? It's feel free to use either formula, and the bottom formula is probably more accurate because it has been obtained by looking at actual data and looking at simulation results. It's okay? All right. Now, one interesting thing to point out is that from the theory of VT we have, remember what VT is. VT is equal to VFB plus 2 phi B plus, let's say QB divided by Cox. Let's look at that, all right? It's okay? Okay. Now, roughly speaking, suppose we change the we try to play with XD max. You say, well, the smaller XD max, the better, right? Well, suppose we try to play with that, and the standard way of trying to reduce the XD max would be to increase the doping concentration of the body. Is that right? Right? If you increase the doping concentration, what's going to happen is that this term is going to increase. You see that? Yes? Right? If this term increase, QB increase, and if you had a certain VT goal that you're trying to meet, that's usually the case, right? We cannot accept any VT you give by using very heavy doping concentration, and you end up having a transistor with 3-volt VT. Nobody can use that, of course, right? So the only way to accept a heavier doping concentration, which will give us larger QB, is to increase the aux. See that? Such that this term does not increase. You see that? I'll leave this as a exercise for you, and see if you can confirm that for given VT, if VT is given to you, then the XD max and oxide thickness will be proportional to each other. In other words, you cannot arbitrarily choose a doping concentration to make XD max small. You see what I'm saying? All right? And in fact, if you want XD to be large, of course, which would be a wrong thing to do, you cannot even do that. If you want the right VT, there's only one particular doping concentration together with oxide thickness will give you the right VT. See what I mean? And the doping concentration would fix the XD max. So in some way, this result is even simpler in that XD max and oxide thickness are not independent variables, roughly speaking. You see what I'm trying to say? I'm trying to simplify the story for you even more. So suppose you say XD mass is proportional to Tox, then the decay length is simply what? Proportional to Tox. That's the thing. So that just shows the importance of making oxide thin. Clear? All right. If you use the second formula, then you still end up with decay length proportional to oxide thickness and also proportional to xj to the 1/3. So if you take from this the conclusion that it's very important to scale down oxide thickness, that's very good message. You do keep hearing that it's very important to scale down the junction depths as well. Nothing wrong with it. But quantitatively, it's not as beneficial to reduce the junction depths as opposed to reducing oxide thickness. All right, so oxide thickness will be our first weapon, but thinner junctions always helpful. Okay, all right. And okay, so at this point, then I'll point out, this is perhaps a little non-intuitive, and this could be the danger of taking this model sort of at its face value. Because sometimes when a person looks at this model, there are two possible misleading message. One misleading message is that the significance of channel length, right, is that the CD is linearly related to the channel length. Now we know it's not. Exponential function of channel length. We've seen that before, right? We interpret that as representing the CD. Is that correct? Now similarly, and the reason that it may not be so intuitive is that this is not a parallel plate capacitor. So when you think of that way, you get some wrong ideas about the quantitative dependence relationship between CD and channel length. All right. Another thing that's not so intuitive, and perhaps at first look will give you this impression, is to say CD is say linearly proportional to this junction depths, because you would visualize this junction depths, becomes the size of that capacitor plate. Yeah, you follow what I'm trying to say? You might get an impression. Now, this concept is totally not supported, whether you use simulation, you use any other solution of a 2D Laplace equation problem, such as separation variable or whatever. You would not find that this capacitance is linearly proportional to xj. And indeed, you can interpret as this being the CD term. All right? Kind of related to CD, put this way. So the effect of the junction depth is not the same as the effect of oxide thickness. It's weaker. All right? Oxide thickness certainly, well, I would not let's not get into more of that, but just I just want you to remember that this is a useful relation to remember. Xj to the 1/3, oxide to the 1 power. And this the model that I suggested to you about thinking of these 3 capacitors fighting against each other is a very good model, but watch out for the pitfall of thinking that there's a linear dependence on L, or there's somehow some kind of linear dependence on Xj, all right? Watch out for that, all right? The fact that this 1/3 term of Xj shows up in this exponential term means, it's still a very strong function of Xj, of course. It's just that it's not the same as oxide thickness, okay? All right. Any questions about short channel effect? So this is a kind of basically a summary of short channel effect, all right? All right, so let's just push this idea of the importance of oxide thickness as an important thing to reduce in order to support the reduction of channel lengths a little bit, all right? 2 ways to emphasize that. One way is to say there's this concept called vertical scaling. That is, if we want to scale the lateral dimension of a transistor, namely channel lengths, we also have to scale the vertical thicknesses. Oxide thickness is one, junction depth is another, all right? Another way to emphasize this is just look at this historical review. And I call this discussion a simple physics of MOSFET scaling. Once in a while, you see people ask this question, just what is the minimum channel length, right? What is the limit of scaling? And we're not talking about lithography and all that. Let's assume those things eventually can be improved. Etching technology will be there. The lithography in technique will be there. But what's the physics limit that limits the channel length, right? So there's several things we can talk about. The analysis usually go this way. The speed and noise will set some kind of minimum voltage. Right now, for example, it appears 1 volt. It's very difficult to go beyond that. I mean, it's not impossible. We will see 0.8 volt circuit sooner or later. But it's getting very difficult thinking about how to design circuits with a voltage much lower than 1 volt, right? So from this consideration, there's always some kind of voltage limit. Let's say it's about 1 volt. Is that right? And once you know this minimum voltage, you end up with some kind of minimum oxide thickness. And maybe it's because reliability, maybe it's because leakage current, whatever. So once you have fixed your minimum power supply voltage, then you say, oxide thickness cannot be any thinner than that. All right? Okay. Yeah, question?
It seems like the selection of 1 volt is very much a function of VT. So if you could have everything, let's say there was no leakage issue, and you had very reliable transistors with 0.1 volt VT, then you could actually operate circuits more easily at less than 1 volt.
Correct. That statement is correct. One of the reasons we cannot use a lower power supply voltage is because of speed, as we said, right? And so the comment is totally correct. The reason we cannot accept arbitrarily small voltage and still maintain speed, one of the reasons at least, is that we cannot accept arbitrarily small VT. An example he uses perfect one. Right now, no one sees how we can tolerate 0.1 volt VT. It just gives us too much leakage current. This is the point we've seen already, all right? Yeah. So put all this together, let's say 1 volt is a number. I just use example. If you want to choose 0.8 volt, no problem. That we can use that number also. Yes?
Generally, when you reduce the supply voltage, there is a tendency of reducing the speed, right?
That's absolutely correct.
So could you give me an approximate graphical relationship?
I would ask you to wait. That's certainly the topic that we will cover later in the course, as you can imagine, right? And in fact, you probably wanted to hear that before we talk about what's bad about short channel transistors, namely the short channel effect. But textbook following that order, so we'll go in that order. After this, we will talk about what's good about short channel transistors. For example, we're going to come up with more accurate model for the IV curve again. And from that, we'll talk about what about speed, all right? So we'll get to there. So from speed noise consideration, there will always be some kind of a voltage we think we're going to accept as the minimum for at least this round of discussion about minimum channel length. And once you know a minimum voltage, there will be some kind of minimum oxide thickness, perhaps from reliability considerations. And once you know the minimum oxide thickness, you will know the minimum channel length. That's just from the reviewed last slide. You see? You see what we're talking about? In the last slide, there's no ifs and buts anymore, you see. Although here I emphasize this proportional sign, we actually know the parameter, not just proportional. 0.1 here, there's no unknown here at all. If you know the oxide thickness, you will know what decay length is. Is that right? Yes? And it's trivial to say that you can only tolerate probably L has to be at least, say, 3 or 4 times larger than this decay length. Otherwise, this quantity will be too large, such that delta VT will be, say, 1/3 of the power supply voltage or something like that. That's way too large. You see what we're saying? Yes? Do you see what I mean? If this is 1 volt, this is 1 volt, and we want to keep, if VDS is 1 volt, plus 1 volt is 2 volt, if we want to maintain delta VT at 0.1 volt, we talked about this last time, then this quantity better be what? 0.05 or something, right? In order for this to be 0.05, L over the decay length must be what? Probably 4 or 5. Is that right? Right? So this is very quantitative models, no ifs and buts, right? So if you know the oxide thickness, you know the decay length, you know the minimum channel length. Yes? All right. So that's the way to answer the question, what is the physics limit of the channel length, right? So for example, if we combine this discussion with what we just talked about in the last slide, minimum channel length will be proportional to Tox and Xj 1/3. In fact, we even know the number here. If we replace this with equal sign, I'll leave that as exercise for you, right? You should be able to come up with a number here, not just the proportional to. Is that right? Okay. So, if you then look at the literature, you know, this question has been asked many times. There were very thoughtful papers published. You know, once every few years, someone would do such a study. And in the 70s, generally, it's agreed, oh, channel length will not go below 0.5 volt. In the 80s, a lot of people think it must go below 0.2 volts. And today, you know, 0.1 volt is given. The question is how much smaller than that. So the question is then, how did this past projections err, right? How come people didn't know how to answer this question? You know, I made it sound like it's a fairly straightforward question. You should be able to answer this question in 2 minutes, right? How come? Well, it turns out the hardest part of this 3-step, turns out is the second step, all right? The first step is, you know, pretty early on, people always felt probably 1 volt is reasonable number. It's true. Right now, we're trying to push down even lower, of course. We don't know how much lower we can push. You know, maybe 0.5 volt is reasonable. Someday, we don't know for sure yet, right? So that first step is not too difficult. Turns out the third step is not that difficult either. You know, people don't have as clear answer as what I talked to you about until last few years recently. But certainly, people could have obtained this relationship by using, say, device simulators, right? You put in the oxide thickness, then you'll be able to figure out what's the minimum channel length you can get and still not seeing too much short channel effect, all right? Turns out it's the second step that's the hardest to answer. If I tell you what is 1 volt's minimum channel length is the power supply voltage, and I ask you what is the minimum oxide thickness from reliability, well, it turns out in the 70s, people really thought, gee, they're going to need, say, 100 angstrom or something like that, or 200 angstrom. Now, you believe me, at just in the 70s, 100 angstrom sounds like just a myth. How could we ever use oxide as only 100 angstrom in thickness, right? Of course, people were wrong. We don't need 100 angstrom to meet this 1 volt power supply voltage. And why couldn't people find out very easily? Well, we'll talk about that as another topic later in the course. In fact, that would be the last topic we'll discuss, is thin oxide, right? The hint is that reliability is a very difficult problem to deal with. You have to say, you have to guarantee it's reliable for 10 years. We don't have 10 years to do that testing. So how do you figure out how thin oxide is acceptable? It's very difficult, all right? And by the 80s, people figure out, gee, you know, looks like thinner oxide is acceptable. Maybe 70 angstrom, 60 angstrom is acceptable. Well, then we felt that the 0.2 micron is acceptable. Today, of course, we're already using 20 angstroms. So this is just this kind of stories I use as example to emphasize the importance of scaling oxide thickness to scaling channel length. So when you talk about transistor scaling, you're almost talking about oxide scaling to begin first and foremost. All right? Okay. Question?
Probably should know this, but
All right.
what is the atomic radius?
3 angstroms of SiO2. If you look at the average size of SiO2 molecule, 3 angstrom. All right? So when we talk about 20 angstrom, we're talking about maybe 7 layers of molecular SiO2 molecule. All right. Okay, yes.
I saw somewhere that the oxide thickness can go down to about 12 angstroms or something. In that case, you have about 4 SiO2 molecules.
Yes.
And it's sort of hard to believe that that can even contribute to a band structure that we draw. So how would that be?
All right. Let's just focus on this, what you're specifically asking, that you're asking about band structure. For example, can we really visualize the MOS as having such a band structure when this oxide is only 3 layers of, 4 layers of atom in thickness? Do we know the property of the SiO2? This is really a surprising thing. You know, when I was a student, professors always taught us, you know, there's a layer of SiOX at the interface of silicon and oxide. We don't know what it is. Let's don't even go there. Don't touch it. It's terrible material. You know, that's why we need 1,000 angstrom as the SiO2 to get good properties. And you know, we don't know what junk is at its interface. It's a transition region, right? But the funny thing is that from what we know today, this oxide quality not only is extremely good in this 30 angstrom and thinner regime, and in fact, everything we see is as if it's same property as thicker oxide in terms of barrier height to the extent we can determine them, dielectric constant, and nothing seems to be changing. All right. Now, I personally don't know how to really justify why there's not more of a transition layer. But definitely, it's a very good transition. From TEM picture, by the way, and you know this probably better than I do, you can certainly see extremely sharp transition, right? Which I know does not necessarily mean you immediately go into a good amorphous SiO2. But the electrical property of this thing SiO2 is extremely good. If you look in the literature 10 years back, a lot of literature just assumed there's interfacial transition layer, that anything is a fair game to assume about that. But today, we actually assume the opposite. That is, we assume everything is unchanged in this very thin oxide compared to their thicker counterparts. Okay? All right? Okay. All right, this I don't think we need to review, so let's move on to the new section, 5.2.2. What we just finished talking about is called a short channel effect. And related channel effect is something called a narrow width effect. That is, what about the transistor with small w? Okay, let's not worry about a small l. Let's say L is not too small. In this section, this L is just, let's say, 1 micron, 5 micron, not small. But width is very small. 1 micron, 0.5 micron, 0.3 micron, very small width. Visualize that? Okay. First, let me look at this diagram. It's a cross-section of a transistor in a direction that you're not familiar with. So let's spend a moment looking at that. What we're doing is we're taking the cross-section of the transistor in this dotted line. This diagram is looking at a transistor from top down, all right? I guess we haven't really drawn this picture together in this course, so let's look at that. Look at the transistor from top down. What you see this dark line is the polysilicon gate. All right? To one side, you see the source. To the other side, you see the drain. I call them M plus source and drain. Is that right? Okay. Now, sometimes this source drain region, or let's say, okay, I will not introduce it. Anyway, let's just say this is what it is, all right? What defines the source drain region is the following. That is, outside the source drain region, if I, at the risk of complicating this, let me complete this box that encloses source drain region, completed for the portion that's hidden by the polysilicon gate. If I complete that, well, it turns out there's this region that you can visualize that's rectangular, all right? This whole region, sometimes it's called active region. What defines this active region is what's outside. Outside this active region is called the field region. Now, the word field is not new to you. You should have already finished reading that chapter 6 that has to do with isolation. So outside is called the field region. Is that right? What is in the field region? It's a thick oxide. Is that correct? All right. So enclosed by the field region is this active region. And active region are further divided into 3 parts. One part is the channel that's defined or covered by this polysilicon gate. The 2 other regions are the source and drain regions. Okay, is it clear, this picture? All right. Next, let's think about the started line across this transistor through the middle of the polysilicon gate. All right. Now, if we draw the cross section along that plane, this is what you see. Let's visualize this. Okay, feel comfortable with that. All right. Here's the field oxide. Here's the field oxide, and this is the thin oxide, okay? Here we exaggerate the thickness of the thin gate oxide. You know, this is that 100 angstrom, or 20 angstrom, or 12 angstrom oxide we just talked about a while ago, all right? That's what this oxide is, very thin gate oxide. Underneath is the channel region, all right? On top of is the polysilicon gate. The polysilicon gate always overlap the edge of the channel onto the field region. There's always this little overlap. Okay? So the entire channel region is controlled by the polysilicon gate. Now, question for you, if you can answer this question, then you definitely know what this picture is about. Where are the source and drain in this diagram? In this cross section, where are the source and drain? Yeah, what do you think it is?
In front of and behind the page.
That's right. It's in front and behind the paper. Okay? All right. So this is the picture we think of when we think about a short channel effect. Now, the behavior is that as we reduce the channel width, it's known that threshold voltage also change. Classically, the short channel, the threshold voltage tends to increase with W. So this is the kind of the classical assumption about how the threshold voltage vary with channel lengths. And when this behavior is reversed, sometimes it's called reverse narrow width effect. But let me tell you that the world is really changing such that don't assume that for some reason VT going up is normal, and when VT goes down is abnormal. And in fact, both are very commonly observed, and perhaps the VT going down is a more common behavior now. So don't be misled by this terminology. One is the narrow width effect, one is the reverse narrow width effect. Just say that VT is a function of W. VT can change when W becomes very small. When W is large, VT is independent of W, which is what you expect, right? But when VT is small, W is small, VT starts to change. Now, why does it change? What could happen? Well, one way to visualize the increase of VT is the following. It's kind of visualize the transistors being made of several parts, right? There's a part in the middle, there's some part near the edge of the transistor. At the edge of the transistor, there are 2 things that tends to make threshold voltage large. One is oxide thickness is thicker. When oxide thickness is thicker, VT tends to be larger, right? Yes? And secondly, the doping concentration tends to be larger. And this is because we want a large field threshold voltage from chapter 6 reading, right? So for this reason, the near the edge of the transistor threshold voltage is always larger, and the channel tends to be smaller, right? And when we have the transistor that's very large, and we only really see this very large W, then we only see this part of the transistor. When we start to push the field oxide closer and closer in, making W smaller and smaller, we really cannot separate these three parts easily. They kind of all lump together, give us one solution. And the best way to visualize that, if this helps, it's great. If confuses, then just ignore what I'm saying. Best way to visualize why you cannot just think of the transistor as being made of three transistors, one VT, one lower VT, two larger VT. If that's the case, then you will say, gee, VT is determined by the lowest of the three VT values. You cannot really think that way, because you have to think about this concept of energy band diagram as what determines the VT again. Right? When the energy band diagram is pulled low enough, when the barrier is pulled down enough, you get threshold voltage. Is that right? So if these two boundary conditions are now pulling this up, pulling the band up, then even the threshold voltage of the center portion will rise. You see what I'm saying? In other words, the threshold voltage is not just simply a function of the local doping concentration. It also has to do with what doping concentration around it, because you have to solve the Poisson equation in this W direction. Last hour lecture, we solved this Poisson equation along L direction. Is that right? We're not going to solve it for you along the W direction, but I'm asking you to think you can extend the concept learned from last hour. That what determines the threshold voltage is how much VG takes to lower this band. And how much to lower this band depends a lot on the boundary condition. All right? And depending on what this boundary condition closing or far off. I drew this band right. This is probably confusing you. I'm sorry. What I have drawn really is that, you know, it's more like this, the band picture. I'm sorry. Did I do this right? Because this VT, if you want to visualize it, probably you want to visualize this way. It's more heavily doped P here, heavily doped P, more lightly doped P here. Is that right? Is that correct? Yes? All right. So this is the case at the so-called flat band condition. Is that right? All right. However, at a certain voltage very close to VG, let's say, we start to apply positive voltage now in an attempt to lower this value, right? We're going to try to pull VC close to Fermi level, EF. Is that correct? Is that right? We're trying to do that, okay? So now let's visualize with me, all right? When you do that, you apply certain VG, yeah, you succeeded in pulling lowering the VT lower here. Got it? Yes? What about this part? Do you lower the VT, the EC, by the same amount over under the field region, or lowered more or lower less? By more or less, I mean the length of this arrow. You see, let's say with certain applied VG, we're able to lower the EC by this much, by the length of this arrow. Do you think we'll be able to lower the EC by a larger amount or smaller amount? You don't see this, all right? Okay, thank you. All right, let me repeat that. To think about this problem using the concept learned from the last lecture, let's think that we have an energy band diagram. Here I'm drawing an energy band diagram. I drew the EV closer to the Fermi level under the field and farther away from the Fermi level in the channel region, because under the field the doping concentration is heavier, more p-type, right? P plus. This is P minus, so P. You see what we just drew there? All right? Now this is the case for, say, flat band, when VG is equal to flat band voltage. Now that's not interesting. Now I want you to think we are applying a positive VG, trying to invert the channel. All right? And we almost succeeded, all right? By trying to invert the channel, meaning we're trying to bend this EC, pull the EC closer to Fermi level. That meaning inversion. Is that right? Is that right? So let's say we're applying a certain VG which is sufficient to lower the EC by this amount, by the amount that I just indicated with this arrow here. All right? My question for you is that will the EC be pulled down by the same amount over the field region, or by a smaller amount, or by a larger amount? Is it easier to bend this band over the field by a certain VG, or is it harder to bend the band? Harder to bend. Why is that? The answer is correct. Could you elaborate on why?
You said it's P plus, so the
I said, yeah, speak into the microphone, please.
you said it's P plus, so the limit it works.
Wonderful. Anytime the substrate is doped more heavily, it will be harder to bend the band. Isn't that right? That's great. There's another reason why it's harder to bend. What's the other reason? Oxide thicker, that's the other reason. Absolutely right. So the bands here will be more stubborn. It's harder to bend it. Is that right? Is that correct? Yes? Yes? Now think about the way to get this profile is actually don't look at the band bending locally. We have to solve the Poisson equation. This is the concept you learned from last lecture now. Now can you visualize the Poisson equation solver will give you, if W is small enough, will give you this solution. That is, even the band bending in the middle region of the channel is not as large as it would be if the field edge boundary condition does not exist. Is that right? If you don't see it, make the W even smaller. Do you see now? The same VG should not be able to bend this down as much. If you still don't see it, why don't we make the W even smaller? This is the exercise I asked you to do last hour to think about a short channel effect, right? If you don't think the drain is going to lower the barrier, make the drain even closer to the source. Same thing here. Is that right? Okay, question.
How abruptly can one actually change the doping like that?
I'm asking you to visualize you can change the doping absolutely abruptly, as abrupt as you want. In other words, there are two questions involved here, and I want to force you to think about the physics, don't think about the technology. Technology-wise, of course, there's always the Gaussian profile, and I know you all know that. But even if we have absolutely abrupt transition of the doping from heavy dope to P to lightly doped to N, I want you to understand that the heavily doped region sites still have influence of this energy band shape. And that change cannot be abrupt because it's determined by solution of the Poisson equation. And Poisson equation is a boundary value problem. Once you fix the boundary value by fixing this EC, not allowing it to vary with VG, it definitely is going to have an impact on the amount of band bending some distance away from it. How much distance away from it? There's going to be decay lengths. We're not going to spend the time to derive the equation now, but the concept should be with you. You should know there's always that decay length involved. Is that right? Okay. So now you would know, you would not ask, gee, even though I have a high threshold voltage region here, the VT here should not increase, so VT is measured at the first VG at which current starts to flow. That would not increase, but the fact is it will. Okay? Can you see that? All right. Okay. So VT will increase as the W decreases. Okay? All right. Now, sometimes we don't see this term often now, which is great, but in literature a few years back you will see people call something called a reverse narrow width effect, referring to this behavior. Okay, this dotted line. Now that can happen for more than one reason, but the main reason is this, and for this reason it happens quite often. This particularly is prevalent in the case of shallow trench isolation technology. From chapter 6, you know, classical isolation technology is called local oxidation isolation.
The recess standard technology is called shallow trench isolation. That is, you actually start with a
Silicon substrate. You would actually etch some of the silicon away, all right? And skipping some of the details, you will then refill this trench with some oxide. And as a result, you end up with what you really want. That is, after you grow the gate oxide, you put the polysilicon gate on, you will have a higher field threshold voltage because you have a thick field oxide. And if you wish, you could also implant this part more heavily, although it's almost not necessary these days because the well doping is already heavy enough, so the field threshold voltage is very high, and the active region threshold voltage is the 0.4 volt that you want. And this isolation technology is called shallow trench isolation. All right, the acronym is STI. Now, in this technology, it's often observed that VT decreases as W decreases. And the hint for the thinking is, again, is VT must be lower near the corner compared to the center region. In other words, opposite situation as in the low cost. In low cost case, we explain the narrow width effect by saying the threshold voltage is higher near the corner, near the edge of the transistor. So here you have to give explanation why the VT is lower near the corner. Now, why is it lower? You know, some people like to say it's because the oxide here is thinner, and they even point out to, you know, a very correct fact, that is because of the oxidation rate dependence at the corner of a trench. The oxide thickness indeed can be and may be a little thinner than in the bulk, but that's not a correct explanation for why VT is lower. The fact that the thinning of the oxide is very much minimal these days. The engineers try very hard to reduce the oxide thinning at the corner of the trench isolation. Not so much because they're trying to, well, this statement is a strange one. I'll talk about later. I'll come back to explain that later to you. But right now, let me just say the main problem we have about the thinning of the oxide at the edge is not the narrow width effect, but because we're concerned about reliability. If 15 angstrom is the oxide we think we can tolerate for reliable operation, we definitely don't want the oxide to be 13 angstrom at the corner. You can see that, right? And knowing how important it is to reduce the oxide thickness in the channel region, we try very hard not make the oxide at the corner thinner than what it is in the channel region. So let's take that out of your mind for now. Let's forget about the fact that the oxide will be thinner at the corner. Can you give me a reason why the VT is lower near the corner? Do you have a comment or question? All right, ask a question.
I have a question about something else.
Ask a question first.
With this technology, well, aren't you effectively increasing your gate oxide thickness by putting all that big chunk of silicon there in between the source and the drain?
No. All right, let's visualize this way. In fact, let's not talk about that. Let's talk about that in a discussion hour. That's certainly a fair question. As I said, any question you have from the reading, bring up the discussion, but let's not continue with my question. So what do you think can explain the lower threshold voltage at the corner? Could you give me, speak into the microphone? What do you think is the reason?
Yes, edge effect makes the apparent oxide thickness.
Now, when the oxide is thicker, right?
The apparent oxide, the apparent capacitance is larger because of the edge effect. So COX appears to be larger because of the edge effect.
Very good. That is the correct answer. You know, it may look strange. You would think that because here the oxide thickness, average thickness, if anything, is even thicker than in the middle of the channel. But the fact is that there is a corner effect that causes all the field line to concentrate on this corner like lightning rod, right? And what this does is that it actually increases the capacitance. If you visualize what capacitance is that capacitance means for given voltage, how much charge is at the surface. That's called capacitance, one concept, right? And if you also remember, each charge is the source or the ending of a field line. So anytime you have a high concentration of field line ending at the corner, you know there's a large charge density. It just help you understand why the effective curve is larger. By all means, if it doesn't help you, well, use your other intuition about electrostatics to explain to yourself why here you actually see a larger capacitance, effective capacitance, right? All right. But certainly, you don't even have to use that word capacitance. The key operative word is that for given voltage, the electric field here is larger in the corner than in the center of the channel. That you probably can see just by thinking of this as a lightning rod. The electric field is larger, right? Next, remember, what causes the band bending is not Vg, but the field in the oxide. If there's a way to make the field at the silicon surface large, band will bend. Doesn't matter what Vg is. You follow what I'm saying? Right? So any points where you have a larger field at the surface, you have more band bending than elsewhere. So now can you see that there's more band bending in the corner for a given Vg than in the middle in the channel? Yes? Yeah? Therefore, the corner will reach 25B before the channel does as you start increasing Vg. Can you see that? Yes? So that's the result of this VT4 off with the narrow W. Question?
So does that mean that the current starts flowing at the edges of transistor?
Absolutely right. It will first start flow there. Truly that it actually start to invert first. All right? And in fact, usually this is only seen during development. By the time the technology is released to the circuit designer to design circuit, you don't see it. But under development, and occasionally as a pathological case, you will actually find the substratal current curve look this way. If you plot log ID versus Vg, you don't see just one simple smooth curve as we expect from the last few lectures talking about substratal current. You actually see additional kink here, sort of. At this point, the current start to increase, but start to turn down this curve, and then rise back up again, and then trace out what's normally expected picture. And when this happens, the interpretation is, you are having a problem where truly you have a transistor have a lower VT. Lower VT here. Because lower VT, the current starts to happen here, therefore it starts to happen at VT1, let's say. Right? This lower VT1. But because this transistor can conduct only very small current, given the small effective W here, right? Just the corner. Yes? Yeah? So the current will saturate, maybe at only 0.1 microamp or something like that, right? Whereas the main transistor continue to stay in the subthreshold region, right? Until we reach the VT of the main transistor, for example, right? So you can have a situation like that. Yes?
So if this is a case for the trench isolation, why that's not a case for the locals?
Very good point. Well, maybe I could, well, all right, I will answer the question instead of phrasing it, all right? Suppose I was thinking how to answer, I'll first answer in a first straightforward manner, then maybe I'll bring up something more subtle. Straightforward manner is this. The question is, suppose there's a kink when there are two regions, low VT region, high VT region. You can see two regions is IV curve. Why don't we see two regions? In this case, we also have a high VT and low VT region. Is that right? If it is, do you agree that it will look like that? That is, first we see the main channel turning on. Is that correct? Right? Then we will see the new transistor turn on, right? But which of these two transistors conduct more current? Earlier I said this probably saturates at much lower value than that. Remember this log scale, right? Because this corner is very small compared to the bulk, right? Is that right? So suppose this is 0.1 microamp, usually smaller than that, and this is, let's say, 100 microamp. Is that right? So we see a little bit. At 0.1 microamp, we start to see one corner. At 100 microamp, we see a corner. So here, could you draw a picture for me? After 100 microamp, if I add another 0.1 microamp, how would that curve look like? Again, remember this log scale. You're already at 100 microamp now. You add another 0.1 microamp, would you see it?
I'm not asking about current, I'm asking about threshold voltage. Because I think that for the locus process, there's also a corner, so maybe the edge effect will.
So earlier we already explained this in two ways. One, it has a thicker oxide, and two, it has this heavier doping, right? It's true that it also has somewhat of a curvature, but this curvature is not nearly as sharp as shallow trench isolation. And I don't know, perhaps you didn't know, haven't heard about shallow trench isolation before. So let me just tell you, without going into detail, this curvature is much sharper than that curvature. That's one reason we moved from the low cost to a shallow trench, so that we don't have waste a lot of real estate in the silicon area going through this transition region between the field and active region. All right. So therefore, the curvature effect here is not so severe. All right. And in fact, what you just asked gives me a very good opportunity to say something for the experts in the audience. You know, there are probably experts such as they want that will say, gee, but we know by making this corner smoother, we can minimize the thinning of the gate oxide, and that's a standard technique to do it. All right? And by doing that, we also end up fixing this VT roll-off problem by fixing this narrow width effect on the VT. So why do you say that thinner oxide is not the culprit? Because I know by making the corner smoother, oxide is no longer thinner, and VT is no longer falling off. Then why do I say that? Why did I say that the VT fall off is did not result from the oxide thinning? Well, I think you know the answer now. That is, when you make the corner smoother, you have minimized this field concentration effect. That's why VT is no longer falling rapidly. But many people miss that point. They just think that because we eliminate the oxide thinning, that's what's responsible for the VT falling. The fact is that between 25 angstrom of oxide and 22 angstrom of oxide, you won't see any difference in the VT. That's a very small difference. All right. Yes.
What process started using, like what generation has started?
0.35 micron is when most company changed. For example, TSMC, a foundry company, changed that. Other companies that are more concerned about performance could have done this a generation earlier. All right. Yes.
Is it possible to choose a combination of L and W such that you don't have VT roll-off, like in the first case?
Can one compensate the one VT roll-off with a VT roll-up? Can one do that by judiciously choosing W and L? It's not a good idea, although you probably can if you want to do it. It's not a good idea. The reason is that W and L has to be left for the designer, circuit designer, to choose. For some reason, I want this W. For some reason, I want that L. You cannot just say, gee, you guys have to use this combination of W and L, and otherwise you're going to see some undesirable VT. So the device technologist's job is to minimize and hopefully totally eliminate the variation of VT as function of W and L. That's the goal. All right. Yes. There's a question or comment here? All right. So that's a narrow width effect. Any questions about width dependence, impact of width on the threshold voltage? All right. Okay. Next section, 5.253, is called a reverse short channel effect. This is a more interesting topic, more interesting than reverse narrow width effect, because it's actually a good thing that we try to take advantage of. In fact, the device designer often goes through considerable effort to try to take advantage of this and optimize it. So what does that mean? That means sometimes we can make the VT increase with decreasing channel lengths. Okay, you notice increase. Eventually, VT will drop. All right? Eventually VT drop is understandable because, you know, when L is very, very small, eventually get almost a short circuit. So you kind of see why VT will have to drop, right? Short circuit means there's no VT, right? But there's intermediate region of the channel lengths where VT actually increases. Now this is nice because if you say, I can tolerate a plus minus 1 volt of VT variation from the VT0, from the long channel VT, if I can tolerate plus minus 0.1 volt, right? If you say that. Yes? Yes? You now can actually at least argue that you can get a smaller L mean or use a smaller L mean than without that VT roll up, without that reverse short channel effect. You see what I'm saying? Right? VT mean is now reduced from A to B. You follow? Yes? So A would be the L mean with the usual VT roll up that we have discussed so far. We discussed in the last lecture, right? That will give you A as the minimum channel length you can use. Yeah? But if you can create a situation where the VT first rises up a little bit, then drops, you could end up with a shorter channel length B as being acceptable for circuit design or for use in the technology. Is that right? Okay. It's for this reason it's a good thing. All right? Now, how do you produce this good thing then? One way of producing this effect is something called a pocket implant or halo implant. What that really means is you add a little bit P plus to around the source and drain. All right. Turns out it's the source side that's particularly beneficial, but for the production ease of production, we usually add this P plus on both the source and the drain sides. Okay. So both the source drain sides, we basically locally increase the boron concentration near the source and drain junction. In the middle of the channel, we leave the doping concentration lighter, but near the source and drain, we make the doping concentration heavier. All right? And you can create that situation also by an angle implantation such that, you know, how to draw this picture is a little bit problem, but we can talk about later. But just right now, let's say we can do this angle with a tilted angle. It's called a large angle tilted eye implantation. In other words, when we implant this P plus region, we don't implant it vertically. We implant it at an angle, maybe 30 degrees from the vertical, right? By doing that, we can deliberately throw this P plus to the front of the N plus source and drain, which is what we want. Remember, we want this P plus to be ahead of the N plus. If it's behind the N plus, we will not see that P plus. Is that right? We'll just be compensated by the N plus dopant. So we use an angled implant to throw this in front of the source and drain junction. Is that right? So either creating this picture or creating this picture, in both cases, one can create this reverse short channel effect. There's a question or comment here? All right. So now the question is, can you see why we can create this reverse short channel effect? Just look at the first part where the VT rise. How can you make VT rise as channel length gets reduced? Just use the concept we talked about before with narrow width effect. Can you see this could give you a VT rise as channel length is reduced? Can you see that? Sure. Your edge now will have a larger channel length. Is that right? I mean larger VT. Is that right? Again, the difficulty of understanding this, student often asks is that, well, that will really not cause VT to increase because I can divide the channel into 3 regions. I have, you know, the normal VT here. I have 2 high VT region on the end. So what? These 2 ends doesn't turn on. The channel will still turn on as before. Is that right? If someone give you this, ask you this question, how would you answer that question? Yes.
Well, if it gets cut off at one point, then it can't flow anywhere. If the current gets cut off at one point.
If that's the answer, then maybe the VT should look like this. It should be high throughout. We'll never go back to this low VT at long channel. Yeah? You see, this is the problem of taking this local view, and that's very good that you brought this up. I wasn't even thinking about that question. Can we really visualize this transistor as 3 transistors in series? I know it's tempting, but I'm trying to preempt that question when you think about it, all right? This is not a good picture to look at. Instead, you should think about extending the lecture from the last lecture to draw the energy band diagram from the N plus source through the P plus, through the P, through another P plus, back into the N plus. If this P plus region is very narrow, will it go to sort of where a uniform P plus would take you? Would it go there? It would not. In other words, this P plus and P all have impact on each other. You see what I'm saying? You cannot just visualize this as 2 transistors in series. Okay? Let me give you one drawing in the next slide to see this is a little better than the freehand I just done earlier. What I'm trying to remind you is that suppose you don't look at suppose the P plus pockets were not there. You just have the N plus source, N plus drain, and P in the middle. From last lecture, can you draw a curve for me representing the potential from source through the channel into the drain? Hopefully what you will give me is this curve, right? This curve here. I'm just tracing over one of the 2 curves here. Hopefully you will tell me this is the correct answer. Now, do you remember this picture? This curve looks familiar from last lecture. Is that right? Is that right? Is that right? Particularly, I want you to remember why this thing doesn't jump up, and then suddenly become flat again and jump back down. This is because this is solution of Poisson equation. There's exponential function of decay length. There's no way for this function to jump up and down as you wish. Is that right? Is that right? So now, knowing that, now we're putting a very thin P plus region. Can you really think that this waveform is going to jump back and back down just as you go across the P plus? After all, this P plus is still falling within this transition region, the decay length, right? So instead, you have to just think we're going to modify that Poisson, that hyperbolic sine cosine function to be more complicated. You may create 2 peaks as a result of the N plus, right? But this peak certainly will not reach the same height as a transistor with just a uniformly P plus doping. You see what I'm saying? Because doping everywhere has influence on this potential profile everywhere else. And it's that final total effect, the highest barrier, wherever that may lie, will give you the threshold voltage. You see what I'm saying? It's correct? All right? Yes? All right? Okay. All right? So it's for this reason that we will have this this effect. In other words, if the channel is very long, we might have a picture like this. We might have a picture like that. There's some effect due to the doping. I'm not trying to say there is no effect at all. There definitely is an effect, okay? That's why even for a long channel transistor, by adding this Paco implant, you will notice already VT is a little larger than without this Paco implant. You can probably believe me, all right? All right? Okay? And certainly technologists will know that sometimes people have difficulty accepting that. But anyway, let me just say, let's take this. This, in fact, is a more intuitive picture. That is, by adding that P plus implant, even for very long L, even with 10 micron long L, you already will see a VT that's a little larger than without a Paco implant at all. That's true. Now, given that's a fact, it's up to you now to explain to me why, as you reduce this L, you will be able to get this VT to increase when the L is very small. I want you to answer that to yourself just by redrawing this, by bringing this L smaller. Your goal is to try to convince yourself by making L smaller, your peak barrier height actually would increase. Now, can you see that? That could happen. Can you see that? When these two bumps overlap, when they're close enough, when they overlap, isn't it possible the barrier will be larger? Do you follow me? Yes? This bump will not increase when it's a 10 micron or 20 micron. There will be no difference. Right? Yes? If it's 10 micron or 5 micron, probably won't make a difference either. But whether it's 5 micron or 1 micron, can you see that there may be a difference? Because eventually the bump might overlap each other, end up with one bigger bump. Right? The important thing is to remember the length of the bump is not equal to the length of this P plus region. That's the important thing to remember, to know. Do you follow me? The bump may be much wider than this P plus region. Right? All right. So this is the way to understand the short channel, reverse short channel effect. And we'll probably spend enough time, so I don't want to get more. But if you don't think this way, you probably will think about some questions that cannot be answered by just thinking them as three transistors in series. All right. One very simple question really is, if you have three transistors in series with 3 VTs, why should the threshold voltage increase as L decreases? Why doesn't it just stay at this highest of the 3 threshold voltage? You see what I'm saying? Why doesn't it stay at 3 higher voltages? So you have to believe that even the barrier at this region is getting reduced just by making the channel longer or smaller. All right? But this picture is perfect. Absolutely no problem. All right? And if I give you a long homework asking you to derive a solution using quasi 2D model, you better be able to do it. Remember how we solved it? We draw the Gauss box. Here you just have add 2 more boundary conditions. Still draw that Gauss box. Solve that the differential equation. Remember we end up with a first order differential equation, not second order linear differential equation. Remember, solution is very simple: hyperbolic sine, cosine. Is that right? So just giving yourself 2 different regions, make the potentials continuous at this 2 new boundary conditions, you get this equation for this profile. Can you see that? For this potential profile. All right? So that's the picture. All right. So the idea is by adding some pocket implant, we can end up with a shorter L mean. One question, maybe just for you to think about, maybe you can answer now. Is it possible by adding some pocket implant to mitigate some of this VT roll-off, this bottom cases without implant? Is it possible by adding certain amount of a pocket implant such that we have reduced this VT roll-off, and yet without producing any VT roll-up, without producing any reverse short channel effect? Do you think it's possible?
Could you perfectly control the doping profile?
Assuming you may.
I think if you could perfectly control the doping profile, it's just like making a filter that doesn't leak.
That's the answer is correct. All right. So you may want to think about this to see if you understand what that means. All right. And particularly if you think of this as 3 transistors in series, would that ever be possible? All right. Now think about that. Okay. If you have 3 transistors in series, would you ever be possible to pick 3 transistors with 3 thresholds such that it give you a certain profile? All right. And then you can think about the more subtle picture that I ask you to think about, and then see if it's possible for you to have a case where the threshold voltage does not really increase, but it will delay or it will minimize or reduce the roll off of the VT. All right. Okay. And of course, this is the beginning really of the question of how to optimize this reverse short channel effect, because the goal really is not to peak too much and to delay this roll off as much as possible, right? So if you are interested in this topic, you have the tool to answer those questions, but we will not go into the details, all right? Okay. Any other questions about reverse channel effect? All right. If not, let's look at the new topic. Yes.
Could we explain why the voltage drops so dramatically after a certain length for the pocket implantation?
Sure. Let's visualize that eventually, let's say, what causes the VT to be very, very low. Thinking about what we said in the last lecture, what will make the VT very, very low? Well, if this 2n plus becomes very, very close to each other, eventually the VT will be very, very low. Can you visualize that? Right? Almost doesn't matter whether this is doped P or P plus. Think about the solution for the potential profile yesterday. The solution, I did not highlight this for you, turns out it's not a very strong function of doping concentration. Yeah, it's a function of XD max. But especially in this geometry, is this depletion region really determined by doping concentration, or is it determined by the junction depth? Right? So even this XD depletion really is not that much a function of the doping concentration in the pocket anymore. Can you visualize that? So given that's the fact, now using the model we talked about in the last lecture, can you see that eventually that VT fall off really is independent of doping concentration? So the fact that we have a P plus really have no impact on it. So you can almost see, finally this will catch up with that, with the original curve. You see that? And this, in fact, is a weakness of this using reverse short channel effect to get a minimum L mean. The reason is we now end up a larger DVT DL. Now remember, I made the argument, large DVT DL is also undesirable. Is that right? Because it means it's sensitive to the manufacturing variation. Lithography, etching will always give you a certain amount of delta L, right? So even if you maintain the same 0.1 micron of a delta VT, you end up with a larger DVT DL compared to without this pocket implant. See that? So that actually is a problem. So then you can ask a question, is it possible for me to minimize this and still also minimize the delta VT? Well, of course, when things get so subtle, you better be able to do something slightly quantitative, and that's where some of these concept quasi 2D equations and maybe spending some time deriving some equation will be worthwhile. All right? Okay. But at least we can talk about some of these things qualitatively now, right? So that's why it will fall off faster, right? Because eventually it will catch up. You can almost see that point. All right. Other questions? Okay, the next topic, according to textbook, section 5.3, is the punch through, all right? And the word punch through, sometimes some people also use a term called bulk punch through and surface punch through, so I'll briefly mention that. But right now let me tell you that avoid using this terminology, surface punch through. Let's reserve the punch through to refer to a bulk phenomena that we'll call punch through, all right? What happens is this, and this usually happens when you, let's say you have done a good job, specifically by good job I meaning by making oxide very thin. If you do a very good job by making oxide very thin, well, the drain will not be able to lower the barrier along the surface because the gate is pulling this barrier up. You see that? The gate is doing a good job maintaining the surface potential, right? Meaning the drain cannot pull this surface potential down, therefore cannot pull the barrier down, right? Because the gate is not allowing the drain to do that. But is there anything to prevent the drain to pull the potential down somewhere farther away from the surface? No. So if you draw the energy band diagram along this profile, for example, along this trajectory, if we draw the energy band diagram, we usually don't draw an energy band diagram along curved line, of course. But if you did that, You draw the energy band diagram along here, right? We had a good P M plus to P barrier, that building potential before. But just because of the capacitance between the drain at this point, and nothing's preventing this to be pulled down because too far from the gate. Is it possible for you to visualize the barrier actually can be lowered more, sort of somewhere here than over there? Can you see that? Yeah? So if I actually draw this energy band diagram along this, you will see that originally it might look like this. You know, before I apply any drain voltage, it's like that. And of course, it's longer trajectory now because it's curved trajectory. So when I straightened it out, I made it longer than the channel length, right? All right. So with 0 VD, this is my barrier. It's very good, right? Because it's a barrier, electrons cannot flow from the source to the drain. Now I start to apply a drain voltage. Can you see that might look like this? Do you see that? Same thing we talked about last time, right? Except this will happen at a lower VD than what causes the barrier to lower near the source. Why? Near the surface. Why? Because near the surface, the gate through the very thin oxide is pulling this surface potential up. It's preventing it from being pulled down by the drain. But in this bulk path, nothing is preventing this to be pulled down. And therefore, current can start flowing in the bulk first. It's not flowing from the surface. We have done our job right. Surface has been controlled very well. Surface potential, surface barrier controlled very well. But current can flow in the bulk. And that's known as punch-through. Is that right? Okay. A punch-through, often people would say, perhaps because some concept they learned from p-n junction, bipolar transistor, something to say when the depletion region from the source touches depletion region from the drain, punch-through happens. That's not a good picture. The fact is that if I ask you to draw a boundary of the depletion region, even with 0 VD, the depletion region already is touched. This whole thing is depletion region. Remember, even with 0 VDS, depletion region is already touched. So how can they even touch more? All right? So that's not a good picture. The good picture is barrier. You have to think about a barrier, right? When a barrier becomes low, you're going to get punched through, right? All right. So let's not use the terminology surface punch through. What controls surface potential is what we talked about last hour. What controls the bulk is a very similar concept, except we don't have that p-n junction, the new oxide's boundary. And in fact, this picture, this energy band diagram is easier to solve. You know, if you ask me how to solve this, I would actually approximate that almost as two almost parallel plated, M plus P, M plus junction. Just solve that. And the third boundary, which is the gate, because so far away, it's not so important, right? With that new picture, just M plus and P and M plus, I will solve at what voltage would I reduce this barrier? Do you see? That can be done, right? It's not too difficult to solve that Laplace equation or Poisson equation for this picture. It's not too difficult, right? Right? And so we'll be able to tell what voltage between this M plus P plus when this barrier starts lower. When the voltage is low, it's not too bad. At some point, it's going to do this, right? And how much voltage will happen, all right? Okay. And that's called punch through. All right. Let's see. All right. Well, almost getting to the end of the hour. All right, well, let me skip one slide. Let me talk about this slide here, all right? How can you tell when you start to see a current flow at low VG, right? When VG is 0, let's say when VG is 0, you're trying to turn the transistor off. You apply 0 VG here. You apply some VD, and current is flowing. So you know there's leakage current. But how do you know it's flowing along the surface or flowing along some bulk punch-through paths? How can you tell? One way to tell is to see whether that leakage current is a sensitive function of VG or not. Suppose you find out this current is not sensitive to VG. You can be pretty sure just from the physics that current is not flowing along the surface, but rather is flowing along some bulk path. Is that right? Along a bulk path, the potential is independent of VG, right? No nothing you can do with VG to either stop that, pull that barrier high or low, right? So when you see the currents independent of VG, you know it's flowing fairly far away from the surface, right? Sometimes you actually see this current totally independent of VG, then you are very certain of it, right? Other times you see this current, well, still dependent on VG, but not as strong as before. Well, you might argue that current is flowing somewhere still close to the surface, but not right at the surface, maybe it's 100 angstrom below the surface. And that's possible. I don't want to force you to think too hard about it, but if you can, maybe you can visualize a three-dimensional energy band diagram, three-dimensional, not just plotting from source to drain, but you know, think about, is it what, well, anyway, I will not go on further. So this slope is a very good indicator of where the current is flowing, because the slope is actually determining, if you remember what determines the substructural swing, the standard swing. Standard swing is determined by ratio between this capacitor and a capacitor that goes to the ground, namely to the edge of the depletion region. Is that correct? Now suppose I tell you, and I'm sorry, when I say this capacitor, I meant the capacitor between the gate and the surface. Is that right? And this is a testing whether you understand the concept of swing now. Suppose I tell you the current is not flowing along the surface, but rather is flowing along some subsurface path that I just drew here. Does it make sense to you that the new swing will be determined by the ratio of this capacitance and this capacitance? Does it make sense to you? Yeah, if you nod it, then you understand the swing. You understand the substructural current, that you're not just reciting the textbook. What determines the swing is really the ratio of two capacitance that are controlling the potential at the current path. That's what it is, right? Potential will mean that barrier height, right? So this actually tell you where the current is flowing. So next time you see this happen as a result of short channel effect, you have some understanding what might be happening. All right? Okay. All right. So another way to represent short channel effect very often, by the way, is to plot swing versus channel length. I don't believe textbook talk about that, so let me just tell you about it now. All right, in the literature, if you look at the papers, often people plot not only VT as function of L, they all plot swing versus L. Guess what that curve will look like? It will be independent of L when L is long, you know, maybe 90 millivolt, whatever, 85 millivolt. And when L gets small, it starts to shoot up, right, fairly rapidly. And guess what? Where it shoot up is very much close to where this VT starts to roll off. Okay? Now, the good thing is that I wanted you to think the short channel effect is all short channel effect. All right, whether it has to do with swing, whether it has to do with VT, whether with something else, they're very, very closely related. Why they're very closely related? They all have to do with this capacitance coupling, all have to do with solution of Poisson equation, all have to do with that barrier height. It's for this reason they're all one problem. Cannot separate them, all right? The impact of the body, impact of the gate, impact of the back gate, and they all relate into one. That's why they all happen at the same time, okay? And so substrate swing is often used as another monitor for the short channel effect. Okay, all right. And it's for this reason, well, I will not go on. Okay, it's for this reason that one can argue, you know, when current does happen, does that necessarily mean immediately we're having bulk punch through? Is it possible we're still having the surface current flowing? Well, that's why I give you this as additional test to answer that question, right? If this swing is still very close, just a little bit different from the original swing, then you know it's still flowing fairly close to the surface. But if you suddenly notice the current is independent of VG, then you can bet it's a punch through deep in the bulk. All right. Okay. So we'll end here, and I'll see you on Tuesday. Tuesdays we'll start a new chapter. Not new chapter. Totally new topic. Section 5.4. That is IV characteristic. So we're going to go over the MOSFET IVs from the beginning.